Okay, so I'm going to do a quick sort of overview of the notes that we've done in the last couple of days. So if you haven't done them, you can stop the video and go over them, but I'll go through them and explain them, and then you can stop them and write the notes. So I've loaded up the notes to print them, and then you can stop them and go through them and write them as we go. Previously, I've done a video on what is matter, and that video goes up through, giving you the notes, up through all matter must have mass and volume. And so today, we took up, is fire, oxygen, gas, or air matter? And what we decided was that fire is not matter, it's actually energy, because it doesn't have mass or volume. That oxygen, gas, and air, both, yes, they are matter because they have mass and volume. So next, we talked about what are the properties of matter and how do we identify them. There are two classifications for the properties of matter. One is physical properties and the other is chemical properties. Physical properties, these characteristics can be observed without altering the substance's identity. So mass, shape, texture, smell, all of these properties, when you experiencing them, the substance doesn't change identity. But chemical properties, for example, flammable, rusting, blowing something up, does it explode? Does it combust? Does it catch on fire? All of these things, when you experience these things, the substance actually has to change what it is in order for you to find out if it has this property. So in order for you to find out if something that is combustible, you have to blow it up. And when you blow it up, at the end of it, the same substance isn't there. So in order for you to find out if dynamite is explosive, you have to blow the dynamite up. And when you're done, what you don't have is dynamite anymore. You have ash, you have gas that has blown away, and so you've created a new substance. So it's no longer dynamite. So in order to experience whether a substance has one of these chemical properties or others, you have to change the properties. So that would be a chemical property. So then the next thing we do is we look at a physical or a chemical change. And again, a physical change, the substance doesn't change identity. So example, if we melt ice, which is frozen water, we still have liquid water. It doesn't change identity. If we dry something or we cut something, it's still the same substance. It's just smaller, or it's dry, or it's a different state of matter. But it's still the same substance. Now, in a chemical change, we're going to actually change the identity of the substance. So, for example, if I burn a log, then I end up with ash. It's no longer a log. If I react a substance and create a chemical reaction, a new substance is created. So the example that I used in class is if I put an Alka-Seltzer tablet into water, when I look at the water, I don't see any bubbles. And if I were to actually put that Alka-Seltzer tablet, like rub it around in my hand or put it up to my face, I certainly wouldn't feel a rush of air or anything coming off of it. But when I put that Alka-Seltzer tablet into the water, suddenly there's a huge rush of bubbles coming off of it, which means a gas is being released from it. So that wasn't happening when I just held it in my hand. But now when I put it in water, a gas is coming off of it. So a new substance has been created. That means that a chemical change is occurring. There is a chemical reaction occurring. And in fact, carbon dioxide is being created, and therefore a chemical reaction is occurring. Burning produces carbon, which was not there before. I mean, it was there, but it was wrapped up in a substance. So because the carbon is being released as carbon, that means that a new substance is being created and released, and so other substances have to be changing. So all chemical changes are accompanied by physical changes. In other words, gases are being created. That tablet that was at the bottom of the water is now disappearing. It's decaying and it's eroding. So all chemical changes are accompanied by physical changes. So something else is occurring besides this magical change that a gas is appearing. Something else must be occurring. So next we talk about that mass cannot be created or destroyed across a chemical reaction. This is called the law of conservation of mass. And it means what you start with in mass is what you're going to end with. So we have an example reaction here. During a chemical reaction, 4.032 grams of hydrogen combine with oxygen to form 36.032 grams of water. What this means is, if I write out my equation, hydrogen plus oxygen makes water, and I have 4.032 grams of hydrogen, and I end up with 36.032 grams of water, the mystery is how much oxygen there is. But I know that what I start with is what I end with. So I take the oxygen, the water mass, and I subtract off the hydrogen mass. And what's left is the oxygen mass. And this is the law of conservation of mass and matter. Notice the the significant figures, 3 behind the decimal, 3 behind the decimal, and then 3 behind the decimal. Next is a sample problem that kids did today in class on their own. They took the 2.445 grams of carbon plus 8.25 grams of oxygen, and you add them together. You get 10.695 grams of carbon monoxide, but as we know, we're going to end up with 2 behind the decimal because of sig figs. The rule that we apply, and that was, so we get 10.70 grams of carbon monoxide. The rule that we applied here for sig figs is that in an addition and subtraction problem, we're going to use the lowest number of digits after the decimal. Now, if you don't remember this, you're going to want to get your periodic table right now, and you're going to want to put this in a little box on the back of your periodic table, because that's what it's for. That's what you want to use it for. So, in a little box on the back of your periodic table, you're going to put, when it's a subtraction and addition problem, we're looking at the lowest number of digits after the decimal. When it's a multiplication and division problem, we're looking at the lowest number of significant figures overall. And if the problem is mixed, you're going to use the multiplication division rules. So then you're going to look at the lowest number of sig figs overall. So in this case, it was an addition problem. So I looked at the lowest number of sig figs after the decimal. But put this on your periodic table so that you have it any time that you need it, all right? Next, the next lesson was today, we looked at percent mass, and this was if I have a compound or a mixture, and I want to know the percent by mass of one element in that compound, or pineapple, the percent by mass of pineapple in a mixture of fruit. I take the mass of the element in the compound over the total mass of the compound times 100%. So, for example, if I have 78 grams of an unknown compound and it contains 12.4 grams of hydrogen, what is the percent mass of hydrogen in the compound? So I take the 12.4 grams of hydrogen, I put it over the 78 grams, which is the total of the unknown compound, and I multiply by 100. Now, significant figures tells me that I'm going to have 3 digits, so that gives me 15.9% hydrogen. Next, another sample. So here in this problem, if I have 3.5 grams of element X, and that reacts with 10.5 grams of element Y, to form compound XY. So what I did was first I set up my equation, and then I added those two together, and that gave me 14.0 grams. And so that was like a law of conservation of mass problem, just like the previous problem, and hopefully you can see that. Next, I took the percent of X, 3.5, divided by 4.0. See that? 3.5 divided by 14.0 times 100%. Notice my two significant figures here. See, two significant figures gives me 25% of X. Now I do the same thing with my percent of Y, and I get 75.0% of Y. So this 0 is because I have 3 digits here and 3 digits here. So I end up with 0. But the rule is that you always look back at your two original numbers, and there's 2 digits in the 3.5. So this should, again, be 75. You always go back to your original digits. So that should be 2. However, the second way to find this, the second way to find your percent by mass, is to take your 100% of XY, because that's going to be 100%, and then subtract off your percent of Y, of X, 25%. Whatever's left is going to be Y, because X and Y add up to the total. So I can just take the 100%, subtract off the 25% of X, and I get 75% of Y, which, by the way, because of the rules of significant figures, the 75% here would only have 2 digits because there's no digits after the decimal for the 25%. Lastly, we did percent error, which we're going to work on more. There was no homework on this, but there is homework on the rest, on the other two, the percent by mass and the law of conservation of mass and the physical and chemical properties. But there's no percent error on this, on the homework. So percent error is equal to accepted minus experimental over accepted times 100. So this is like the accepted value minus the value that you might have gotten in your experiment. So the difference between the two would be your error. And then you take your error and you put it over the accepted value. These are absolute value bars because we don't care whether you're high or low. We just want to know how far away you are. So we take 8.96, which is the accepted density for copper. We subtract off 8.86, which is your experimental value, and we divide that by 8.96. And when we do that, we multiply it by 100, and you get 1.12%. And that is your percent error, which is always positive because of the absolute value bars. So now you're able to fill in your notes, and you got a little bit of an explanation, and you should be able to at least attempt the homework. And so that way you can get caught up and we can work on it in class. I hope this helped.